So again, in the previous video, I was saying that today we have better technology so that now we can avoid such collisions. But it's still a cause for a lot of injuries and vehicle kind of crashes that could happen. They could have in a lot of accidents in this respect, and we could lose a lot of money by these accidents. So an example that I have for current money ways in which fog can affect us is by landing in certain airports. For example, back home, as I was saying, there's a lot of fog, and this fog is very common in the early morning, so right after dawn, which is the highest amount of moisture in the day. This has happened to me many times when I'm landing into Bogota, actually, that the airplane has to either circle the city for a few times to avoid, landing in the fog in the runway itself. And a couple of times we've had to go to a different airport to land there and wait a couple hours until the fog is out of Bogota. So basically by doing so, you're losing money and you're losing time. So those are ways in which fog nowadays can affect us, apart from the obvious, crashing when you're driving and whatnot. So there you go. So drought is the next hazard that we're going to talk about. So drought is officially defined as extended period of unusually low precipitation that produces a temporary shortage of water for different species, may it be plant, animal, or humans. So about 1 billion people in the world live in semi-arid regions where droughts are pretty common. So that's a very high percentage of people, more than 15%, or close to 15%, I should say. About 100,000 of those billion, or more than 100,000 of those billion, are actually threatened with malnutrition or death if a drought actually causes a crop failure to occur where they live. In the U.S., however, droughts cause $6 to $8 billion losses every year, which is major, and they tend, as you might know, also to be more damaging in the western U.S. So we are actually pretty affected by droughts here as well, but they're very common, like in Arizona and California, for example. Also in Oregon, like Eastern Oregon. So mountain windstorms. So usually mountain windstorms develop seasonally on the downwind or on the lee side of mountain ranges. The two examples that I put down here are not probably the best because they are, minor kind of parts of the mountain, but they kind of show you the idea of what a mountain windstorm will sort of look like on the short scale of it. So usually they develop again on the downwind or lee side of the mountain ranges, and they go downslope of large glacial ice fields as well, such as in Antarctica. They're pretty dang common. So Chinooks are going to be very fast winds on the east side of the Rocky Mountains. That's what they're called, these specific mountain windstorms, Chinooks. And again, this in the Rocky Mountains. And they're called Santa Ana winds for the winds that are going off the west side of the transverse ranges in southern California, for example. They're the same type of process, but in different regions they're called different things. They also occur in smaller mountain ranges in the U.S., like the Sierra Nevadas or the Cascades, and internationally they also happen in the Alps, the Andes, Himalayas, pretty much in any major mountain range that you have, the Ural Mountains, whatever it may be, you get them. They are very big contributors to wildfires because usually wildfires happen, or they sometimes happen in mountainous terrain where you have forests, and with this high winds they tend to spread the fires even further. So they're big drivers of wildfires. Storms and sandstorms. So they're basically strong windstorms in which suspended dust can be carried by wind, which reduces the visibility for a significant period of time. For the most part, these storms, although referred to as sandstorm by the meteorologists, they're mostly just dust storms. So they tend to have wind velocities, or they need to have wind velocities that exceed 48 kilometers per hour to be considered officially dust storms. and they have or they need to reduce visibility to be less than, sorry, not greater than, zero 0.8 kilometers. I'll fix that too in a second. So they can be several hundred of kilometers in diameter, and they may carry more than 100 million tons of dust. Along with that dust, they can also carry spores and pollen that fall within, adding to the overall obscured kind of cloud within that windstorm. Most of this suspended sediment that is within the wind is clay-sized, meaning it's going to be smaller than 0.05 millimeters, so pretty small. But that is also partly why it's able to stay suspended within the windstorm, right, and not just simply settle. As opposed to dust storms, sandstorms is only a desert phenomenon. And because sand, for the most part, is also sand-sized, meaning a little bit bigger than clay-sized, at least 2 millimeters or more, then the specific sandstorms have these sand particles only travel about 2 meters each. So it doesn't go very far, and it's not a lot of suspended sediment like the dust storms, but rather it does move them, but not very much so, and they're going to be sediments of larger size. So dust storms and sandstorms, I guess, if they do happen near humans, can affect human health in terms of respiratory problems. They can affect climate by eroding basically at a faster rate, and they can become a travel hazard, obviously, if you are about to be in one of them. So usually they occur in the mid-latitudes in semi-arid and arid regions. This is partly because those mid-latitudes have very dry areas where you can have dust that is loose in the first place. An example of these dust storms and dust storm more than anything, it was the Dust Bowl, as you might have heard of it, in the 1930s. This happened because of poor agricultural practices mostly, so a lot of the plowing practices were not so good, and so there was a lot of loose sediment over the winter that was not, contained in any way. So with increasing in wind and kind of winter and spring actions, this amount of windstorms was just gigantic, and so it affected 5 states in the U.S. For a few years, if I'm not wrong. The picture that you have on your right is from the sandstorm, or the dust storm, sorry, in Phoenix in May or in July, I think, of 2011, which was pretty major. I think they were hit by 2 main storms, one in May and one in July of that year. And as you may know, Phoenix is pretty dry and mid-latitude and arid, so that would make sense. Heat waves. So heat waves are not really heard of too much in the news, but it's probably one of the hazards that kills the most amount of people overall in the world. So heat waves themselves are defined as prolonged periods of extreme heat that are both longer and hotter than normal. So in the US, for example, between 1992 and 2002, an average of 200 deaths happened per year. So between those 10 years, about 200 deaths happen every single year, just in the US. So again, these deaths happen because of heat-related causes. So it might have been, people got like a heat stroke, or it could have been some sort of heart attack caused by the amount of heat, or something like that. It could have been also something else that we'll talk about in a second. But that's just different examples. So just to give you a perspective on how much death that is, about 200 deaths every year happen is the same amount of deaths that happen accounting for tornado, flooding, hurricane, and lightning deaths combined for those same 10 years. So again, if you count the amount of deaths that happened because of heat wave in those 10 years, and if you count the amount of deaths that happened because of those other 4 hazards, tornadoes, flooding, hurricanes, and lightning, then they would be equal. So in that case, heat wave related deaths are a lot higher than the others. An extreme example that I'm going to tell you a little bit about happened in August of 2003. And this happened in Europe, where about 30,000 people died of heat-related deaths in Europe. Again, most of them died in France. I think it was close to 15,000 people died in France, and then the rest of the deaths happened kind of surrounding that country. So they say that 2003 was pretty much the hottest year that they had experienced in what they think was 500 years, and it cost $17 billion to recover from that. So most of the deaths that happened in 2003 in Europe happened because, or near, sorry, cities, and this is because of the urban island effect, which we will talk about in the next slide. But basically, because of this urban island effect, cities actually were 5.6 degrees Celsius higher than the rest of the countryside. So, of course, most of the deaths that you saw were near cities, both because of the amount of heat and because of the stagnation of the pollutants near the city that happen more commonly with heat. So I'll also talk about that in the next slide. So also some deaths happen near the cities because of holidays. So obviously August is a big month for holidays, and so people were visiting areas that were, city-like in the most part. So many of the deaths happened because of that too. It was such a high death count that in fact hospitals and morgues could not really keep up with the sick and the dead people, which was really sad. Another instance in which people died in this disaster was because of the melting of glaciers in the Alps, for example. And so there were a fair amount of avalanches that happened near in high elevation, and also there was a fair amount of mass wasting events that happened due to the melting of the permafrost in those high altitudes. So as we had talked about in the previous chapter on subsidence, when you have permafrost being melted, you have subsidence. And with that subsidence, if it is at a specific slope, then you might get easier mass wasting to occur. So not a lot, but some deaths did happen because of this mass wasting events. So a major disaster. And thankfully now more cities in Europe and also in the US have better warning systems for this type of hazard. So as you're seeing here in the image, we have what is called the heat index. So the heat index basically measures the body's perception of air temperature, which is greatly influenced by humidity. So with higher humidity, the temperature feels warmer. So as an example, in Florida, the humidity is very high. So let's call it that on a normal day, kind of during the day, which should be the driest part of the day, it's still about 75% humidity. So if the temperature in Florida was about 95 degrees Celsius, 95 degrees Fahrenheit, you would have that the overall heat index is dangerous, even close to extremely dangerous. So it wouldn't be very good for people to be out and about during that time. For example, here in Boise, we get very high temperatures during the summer, right? It can hit up to 100 or 110 degrees Celsius even, Fahrenheit, I keep saying Celsius. However, it is not very humid at all. Here the humidity tends to be pretty low. So although we get, say, 100 degrees Fahrenheit, the humidity tends to stay even below 40 degrees Celsius. So we don't often come to this extreme caution or even dangerous state in terms of heat and the heat index. So the heat index is very key, and wherever you are visiting, I would highly encourage you to check it out if you're visiting, especially in the summer months. So there is vulnerability from the less capable and more exposed whenever you had a heat wave, obviously. People that are elderly, babies and infants, the homeless and the poor are very affected by it, and obviously by people who work outside and are exposed to the elements are probably the people who are most vulnerable to these hazard.